Can you see now?
Yes.
Okay, great, thanks. We are good to go.
So then you went to
Hi, I hope you can hear me. Is the screen visible? Yes, okay. So, I'd like to thank the organizers for inviting our work on PIT for non-associative algebras to be a part of this workshop. This is based on joint work with Partha and Pratik, who are in the audience. They're attending the workshop in person. So let me begin first by defining an algebra, which we have seen encountered many times, and then define what a non-associative algebra is, and try to design polynomial identity testing algorithms for non-associative algebras. I can't move the slide.
I think it's fine. It is recorded.
Okay,
Yeah.
I need to share. Some issue. Yeah, is it fine now? You should be able to see. Can't really.
Yes, fine.
Okay, so let's begin with the usual polynomial ring. The ring of polynomials on n variables with coefficients from a field. So in this ring, if you consider both addition and multiplication, both these operations are commutative as well as associative. So by commutative, we mean that the order in which you perform addition or multiplication does not matter. And by associativity, we mean that the grouping of terms during addition or multiplication does not matter. And it is also easy to see that product distributes over addition, that is f times g plus h is just f times g plus f times h. And this ring of polynomials also forms a vector space where the base is the set of all possible monomials of all possible degrees. So it's an infinite dimensional vector space. And polynomial multiplication, you can think of as this vector space being equipped with a product operation, which is polynomial multiplication, and it is a bilinear operation. So it's linear in each of its arguments. And this just follows because product distributes over addition. So this kind of a vector space together with a bilinear product operation is called an algebra over a field. And the dimension of the algebra is the dimension of the underlying vector space. So if you think about the usual polynomial ring, you can think of this as an algebra over the field, which is infinite dimensional, and the product is both commutative and associative. And if you think of this quotient ring, then this is a finite dimensional algebra where the product again is commutative and associative, and the basis is the set of all monomials of degree at most d. There are also some other interesting algebras that we have encountered. For instance, the set of all diagonal matrices. That forms an algebra of dimension k. It's a commutative and associative algebra because diagonal matrix multiplication is both commutative as well as associative. So this is the usual set of examples we see. And multiplication need not always be commutative and associative. So here are some cases where it is not commutative. For example, the non-commutative polynomial ring is an algebra which is again infinite dimensional, where product is both non-commutative and associative. And matrices, the set of all k cross k matrices, they also form a vector space. And matrix multiplication again is a bilinear operation. It is non-commutative, but matrix multiplication is always associative. And this is a finite dimensional algebra. So here are some examples of algebras that are associative, but not necessarily commutative. So if you stare a little closer at this matrix algebra, matrix product is a non-commutative operation, but it is always associative. So you can try to equip the same vector space with a new product operation, which is called the Jordan product. So you can think of this as taking two matrices, and the Jordan product of these two matrices is defined to be half times AB plus BA, where this term refers to the standard matrix product. Right? So if you stare a little closer at A product B, or the Jordan product of A and B and the Jordan product of B and A, they're essentially the same. Jordan product again is bilinear because matrix multiplication is bilinear. But while matrix product was actually non-commutative, you get that Jordan product is commutative. So you have gained commutativity by equipping the same vector space with this new product operation. But is there something you have lost? You have lost associativity. So if you take any three matrices A, B, C, the Jordan product is not associative. And this is not hard to see. It just stems from the fact that matrix product is not commutative. So what we have seen is if you start with a non-commutative associative algebra, which is the matrix product, this Jordan product kind of gives you a way to transform this or get another algebra, which is now commutative but non-associative. And the interesting thing about this is this preserves the dimension of the algebra. Right? So here are some examples of algebras which are not associative but commutative. Okay. So moving forward, let's talk about non-associative polynomials, which will be the central theme of this talk. So you can think of non-associative monomials as monomials that come with some sort of bracketing structure for the multiplication. For example, here are two monomials, x1, x2 is first multiplied, and then you multiply that product with x3. And in the other monomial, you first multiply x2, x3, and then multiply the product with x1. Right? And these two monomials, despite their variable order being the same. So if you think of the non-commutative world, these two monomials would have been the same if you just remove the brackets. But now, after introducing brackets, these are two distinctly different non-associative monomials. And non-associative polynomials are just linear combinations of such bracketed monomials. And non-associative polynomial algebra is this algebra, where product is non-associative. Now, you could think of variables commuting or not commuting. If the variables commute, then here is an example of a non-associative polynomial that is identically 0. Because the variables commute, it does not matter x1, x2 over. The order is x2, x1. And if the variables don't commute, then here is a polynomial that is not identically 0. So depending on whether variables commute or not, you get a commutative or non-commutative, non-associative algebra. Okay. So this is an example of a non-associative algebra similar to the Jordan algebra. Now there are also other algebras. For instance, here there is this matrix Lie algebra, which is the vector space of all matrices. You take K cross K matrices and then define the product to be AB minus BA. This is a non-commutative, also non-associative algebra because you have made the plus minus. This is usually called the matrix Lie algebra. These kinds of algebras that are neither commutative nor associative are usually called relationless algebras. You sort of take the algebra and rip it of any possible relation. Like it's not, product is neither commutative nor associative. These kinds of algebras have been studied. So this is just to say that there are these vector spaces equipped with bilinear product operations, and depending on whether the product is commutative or associative, you get like different kinds of algebras, and there are like very standard examples of these kinds of algebras. And this talk will mostly be interested in non-associative polynomial algebra. Is this okay? Are there any questions? There aren't? Okay. Okay, so let's move forward. Non-associative computation in general is not new to algebraic complexity. It has been studied in the past. In fact, we know very strong lower bounds for non-associative circuits. We know exponential lower bounds from this work of Hrubeš, Wigderson, and Yehudayoff. They exhibit an explicit polynomial such that any non-associative circuit requires exponential size. So this means that over, if you consider non-associative setting, then VP is actually not equal to VN. And not only do we know that, similar to Nissan's characterization for non-commutative ABPs, we also have exact characterizations of the size of the smallest circuit computing a non-associative polynomial in terms of the rank of a certain matrix. So we have very good lower bounds, like really strong lower bounds, and we also have exact characterizations. So you would expect efficient identity testing algorithms, but despite strong lower bounds, we do not know any efficient PIT algorithms. We did not know any efficient PIT algorithms. In fact, even randomized. Even in the randomized setting, no algorithms were known. So in this talk, we will mostly look at PIT algorithms for non-associative polynomials. Okay. So let's take a look at the results first. So the first result is what you would expect, something similar to Schwarz-Zippel in the associative commutative setting. Or if you're a little familiar with non-commutative, something similar to the Amitsur-Levitsky theorem. We are able to give a randomized black box identity testing algorithm that runs in time polynomial in the size of the circuit and the degree of the polynomial. So this works in both commutative and non-commutative settings. So it's a little unclear at the moment what we mean by randomized black box PIT. So this algorithm is given query access to a non-associative polynomial. We're given access to evaluations of this polynomial on a non-associative algebra. So you cannot try and evaluate this polynomial by plugging in field elements or matrices because those are all associative by definition. So you are given query access to this polynomial and you can evaluate it on elements of a non-associative algebra. It is good if it is of low dimension so that the cost of the algorithm is low. And then you have to decide whether it is identically zero or not. So this is the first randomized setting. In the derandomization setting, it's easy to see that you can tweak Hrubeš's algorithm, white box PIT algorithm for non-commutative ABPs to get an efficient PIT algorithm in the white box setting for non-associative polynomials. Now you could also ask, are there efficient heating sets? There are reasonably efficient heating sets, meaning the size of the heating set is NSD with an exponent having the product depth for non-associative circuits. So as long as the depth is little o of d, then you get something non-trivial. If the depth is logarithmic, then this will be quasi. Right? And these algorithms work both in commutative and non-commutative settings. So it's always nice to say that it works in the commutative setting. But it will be instructive to look at the non-commutative, non-associative setting. So this is a overview of the results. If there are any questions, it might be a good time to check. There are any questions? Okay. So the deterministic white box or the Hrubeš algorithm is a little too simple for the audience. And the hitting sets quasi-polynomial size is essentially obtained by you take this non-associative circuit and do an identity preserving summation to an associative circuit with some kind of a structure. It's usually called an unambiguous circuit, if you have seen it in other contexts. And then you obtain hitting sets for those unambiguous circuits by using a technique called the basis isolating weight assignment, which is also by now a fairly standard technique. So it's a little too advanced to describe this in a 25-minute talk for the speaker. The second one is a little too describing the randomized black box PIT algorithm. So the rest of designing a randomized identity testing algorithm in the black box set. Okay, try to design an algorithm. So what is it that we need in order to design a identity testing algorithm? So dive a little bit and come back to PIT after maybe 5-10 minutes. So I want to talk polynomial identities for algebras. So we saw several examples of algebras. Some of them are commutative, non-commutative algebras, polynomial. And we can talk about identities for this algebra. So you say a polynomial is a polynomial for an algebra. Commutative polynomial f, and if f vanishes.
Ramya, I think your internet is a bit unstable.
It shows up as good.
I think, yeah, now I think it's fine. We weren't able to hear you for last probably 30 seconds. Yeah.
Okay.
Would you like to try switching off video? That would improve the bandwidth.
Here. How does it work now? Can't really hear.
Yeah, I think it's better. But you would, I suggest that you turn off your video. Yeah.
Yeah, I just turned off the video. Is it
Yeah.
fine now?
But the slides are
Yeah, now you need to share your screen.
Yeah, how is it now?
Okay, great.
Be
Yeah,
better?
this is perfect. Thank you.
Okay. Yeah, sorry, I think. Okay, so just to get back. So we are going to look at polynomial identities for algebras. So if you can think of a commutative algebra, no matter what commutative algebra you are interested in, then xy minus yx is always going to be an identity for the algebra. This is because you take any two elements in the algebra, xy is going to be equal to yx. Now you can think about matrix algebras, which are not commutative algebras. And here is a celebrated theorem of Amitsur and Levitsky from the polynomial identity theory, where they try to understand polynomial identities for matrix algebras. So here is a polynomial of degree 2k. It's a non-commutative polynomial. And no matter what matrices you plug in, right, this polynomial will vanish on the matrix algebra. And not only did they show that, they also showed that if you take the matrix algebra, it cannot have any polynomial identities of degree less than 2k. So it's sort of a characterization of the minimal degree of identities for matrix algebras. And if you stare a little closer at this kind of a characterization, this will tell you that if you have a non-commutative polynomial of degree at most t, then it cannot vanish on this matrix algebra where the dimension of the matrices is like d by 2 plus 1. So then you can exploit this fact by substituting random matrices of this dimension and obtain a black box PIT algorithm. And there has been considerable work on non-commutative PIT using this kind of an approach for using polynomial identities. These are some recent works. One of them is by Arvind, who also tried to show that there cannot be PIs for non-commutative polynomials where the function is dependent on the sparsity. And then it was recently used to prove polynomial identity testing algorithms for some special class of non-commutative circuits and so on. So this is, you fix your favorite algebra, you can ask what can you say about polynomial identities for this algebra. But so far things were all associative because matrix algebra is associative. But we had these two special kinds of algebras, which is the Jordan algebra and matrix Lie algebras, which are non-associative algebras. And it's not hard to see that these are two identities, which are polynomial identities for this algebra. Meaning no matter what two elements you take from the matrix Lie, what three elements you take from the matrix Lie algebra, it will always satisfy this identity. One thing to note here is that these identities have constant degree. Like this identity has like degree 4 and this identity has degree 3. That's something that will come up again. Okay, so we sort of digressed a little bit, but it's useful to see that you can use these kind of statements about polynomial identities for algebras to obtain randomized PIT algorithms. Now we need to turn our attention to non-associative circuits. You can think of the circuit as being non-commutative or commutative. So let's consider the non-commutative case first. So let's say you are given a non-commutative, non-associative polynomial. So the variable order matters and also the bracketing. And this polynomial has degree at most d. And you want to test whether it is identically 0 or not by querying this polynomial on elements from a non-commutative, non-associative algebra. So the first thing that you would probably try is take known algebras that are non-commutative, non-associative and try to query f on those evaluations. Right? But the bad news is that from the previous setting, we know that there are these very low degree polynomials which are identities for such algebras. In fact, most of the known non-commutative, non-associative algebras satisfy low degree polynomial identities. And then you cannot query from that algebra. So this requires you now to design an algebra which is non-commutative, non-associative and also of low dimension, such that you take any non-commutative, non-associative polynomial. This polynomial should not vanish on the entire algebra. In other words, f should not be a PI for this algebra. Then you are in good shape because now then you can sort of try to use random elements and get a randomized identity testing algorithm. So for the rest of the talk, we'll try to design this algebra. So what is it that we need to do to design such an algebra? First, I need to tell you what are the elements of the algebra. It's essentially a vector space. So I need to tell you what is the vector space. And then we need to define the product operation. You must also ensure that this product operation is bilinear so that this whole thing is actually an algebra. And you need to ensure that this product is non-commutative and non-associative so that you get a non-commutative, non-associative algebra. You need to ensure that the dimension of this algebra is not too large. It needs to be polynomial in D for every choice of D. And then there's this other stringent requirement that says that you take any non-commutative, non-associative polynomial of degree at most D. This polynomial should not be an identity for this algebra. I mean, no polynomial, non-associative, non-commutative polynomial of degree at most D should be an identity for this algebra. So these are some requirements that you get from constructing this algebra. Once you have such an algebra, it's not very hard to see. So once you have such an algebra, you can define this algebra over a function field by taking in a new commutative associative set of variables and use the usual polynomial identity lemma. So this is by now a relatively standard technique. It is used even in non-commutative identity testing. Eventually you reduce everything to Schwarzschild. Right? So this itself looks a little involved, where we have to construct such an algebra. Now, this is in the non-commutative setting. But what would you do in the commutative setting? But the commutative setting now looks a little easy if you have already designed a non-commutative, non-associative algebra, because similar to the Jordan product that we saw, we can now define this new product by using the same vector space. And then this new product is now commutative, but it is still non-associative. And now you need to show that this algebra does not have any low degree identities. It's not very hard to show this. So what you need to figure out is, suppose it really did have an identity of low degree, then you can sort of take that identity and tweak it a little bit and get some symmetrized version of that identity, which would then be an identity for the originally constructed non-commutative algebra. But from this we know that the non-commutative algebra does not have any identities. So in essence, if you solve the non-commutative version, you get the commutative version for more or less free. It's not entirely free. There is some work, but it's not much. So the whole effort goes into now designing a non-commutative, non-associative algebra of low dimension that does not have any low degree identities. Okay, so in the remaining few minutes, maybe we'll try to design a non-commutative, non-associative algebra. Looks a little demanding. We have to construct the elements, I have to define the product operation, and I need to also ensure that the product operation does not commute, is not associative, and it does not have any identities. So in 7 minutes, how do you do that? And possibly flash the algebra and the product operation, but maybe I should, it's a little embarrassing for me to do it. So we'll look at structure of non-associative, non-commutative monomials and then get back to how to design this algebra. So what is a non-associative monomial going to look like? Non-commutative monomials, we know they are going to look like words or strings in x1 to xn. You can view any non-associative monomial essentially as a tree or a rooted binary tree where the leaves are going to be labeled by variables. Right? And if the monomial is also non-commutative, there is also a variable ordering that comes up. So here are two distinct non-associative monomials and they have two distinctly different trees. One of them is represented by this tree, the other is represented by this tree. So they correspond to distinct trees. And what is that information that you can use to say that these two monomials are actually distinct? So if you tell me the left to right variable ordering, if you tell me that the first leaf from left to right is I1, and the second index is I2, and the third is xi3, there are two trees with the same left to right sequence of variables. What distinguishes these two monomials is the level in which each variable appears. If you tell me that I1 appears in level 3, I2 appears in level 3, and I3 appears in level 2, then here is this unique binary tree that you can draw with this variable order information as well as the level order information. So this is kind of a unique signature. So this order and level information together can like uniquely determine a non-associative, non-commutative monomial. So this is all the information you need to tell me for me to reconstruct the entire non-associative monomial for you. So we need to somehow use this to construct the algebra. So how are we going to do that? So here is your usual non-commutative, non-associative monomial, and here is the tree corresponding to that monomial. The nodes of the tree are leveled. The root is at level 1, and then there is level 2 and level 3. Some variables appear at level 2, some variables appear at level 3. You can encode this entire information into a commutative associative monomial. So you introduce a new set of variables, z variables. All of them are commuting, all of them are associative. The first index tells you what is the variable. The second index tells you what is the order from left to right in the monomial. And the third index tells you the level at which this variable appears. So xi1 is the first and it appears at level 2. So you put in the variable zi1, 1, 2. xi2 is the second variable and it appears at level 3. So you put in variables accordingly and you multiply them. You get a new monomial which is now in commuting associative set of variables. So you have transformed a monomial from a non-commutative non-associative setting to a commutative associative setting. And the advantage of this is that if you have two distinct monomials which are not associative, then they will map to two distinct monomials here. So this map in some sense is injective. And you can extend this map by using linearity. So this map is also identity preserved. Okay. So we wanted to design an algebra, and what we have done now is design some kind of a map that takes non-commutative non-associative monomials to the commutative associative setting. And this map is also identity preserving. So how are we going to try and use this to construct the algebra? Right? So we needed to construct an algebra such that you take any non-commutative non-associative polynomial of low degree. You can always find some evaluation points in the algebra such that f does not vanish on them. So if this evaluation points and the product operation of the algebra somehow captures this symbolic map, then since f is not identically 0, you know that phi of f cannot be identically 0 because this map is identity preserving, and then this evaluation will not be identically 0. But this is if everything works out. Okay, so now let me flash the algebra to you. So you can think of the elements of the algebra as matrices which are stacked one behind the other. So there are D matrices, and each matrix has dimension d plus 1 by d plus 1. So each is a d plus 1 cross d plus 1 matrix, and there are d many such matrices. And so you can think of this as a vector space roughly of dimension like d times d plus 1 square. So that's how each element is going to look like. And now I need to define the product operation. So one way to think about it is you wanted to define a non-commutative algebra. So you need to somehow bring in matrices. It will be useful. You also want the algebra to be non-associative. So you have this third dimension which is going to stack matrices in order to ensure that there is this dimension here which is going to keep track of the level apart from non-commutative setting. Right? So we need to now see how this is useful in PIT. In particular, this is an algebra. First, it's not clear if it's non-commutative, non-associative. The dimension seems to be polynomial in D. And I need to define a product operation and also show that there are no low degree identities. So maybe I'll take 2-3 minutes to do that. Okay. So what is it that you are given? So if you step back and look at it, you are given a non-commutative, non-associative polynomial. It has degree at most D. Right? And it has n variables, xi1 to xin. In these places, you are going to now substitute elements from the algebra. And each element in this algebra is a stack of D matrices of dimension d plus 1 by d plus 1. You can think of these as some kind of symbolic evaluation points. And what comes out after you evaluate f at these points is another element of the algebra, which again is a stack of matrices, D many matrices, each of dimension d plus 1 by d plus 1. And if you somehow are able to ensure that one of the entries here is the map applied to the polynomial, then you can be sure that whenever f is not identically 0, this is not going to be identically 0, and hence this evaluation is non-zero. So what are these evaluation points? For each xi, I have to define what is that symbolic evaluation point. Here are these matrices. These are not fancy or scary. So if you have already seen Forbes-Pilka's non-commutative heating sets. This is some kind of a three-dimensional version of that heating set, where only the superdiagonal elements are filled, and you take the kth matrix and fill the j plus 1th entry with zijk. These are a fresh set of commuting associative variables. You just plug in these variables, and then for each of the xi's, and then now you need to argue that f, when evaluated at these points, will sort of isolate this non-zero element. So I have a couple of slides. How much more time do I have? I can't really see. Maybe 2-3 minutes? Over time?
1 more minute maybe?
Okay. Okay, sure. Okay. So maybe then let's just skip a little bit. Okay. So something that I did not do, wanted to do but I couldn't, is how to define the product operation for this algebra. So you have these D many matrices, and I have two such stack of D matrices, each of dimension D plus 1 by D plus 1. And how am I going to define the product of these? You take the kth matrix of this product to be the product of the k plus 1th matrices from the stack and multiply them together. This kind of will break the non-associativity, but there is still matrix multiplication involved. So it is also a non-commutative algebra. It's a little less time to describe why it is non-zero, but maybe I will leave you to believe that if you sort of evaluate the polynomial on these points, you can isolate in the first row D plus 1th entry of the first matrix a homogeneous component of this symbolic map, and hence this algebra cannot have PIs. So there aren't like many questions that stem up directly from this. One question is, we did show that there's an algebra of dimension roughly D plus 1 square times D. Can you reduce this dimension? For example, if you look at matrix algebras, there is an exact characterization by Amatsur and Levitsky. But you can think of this talk more as an invitation to this area called polynomial identity theory, where you take your favorite algebra and look at all polynomials, the set of all polynomials that vanish from this algebra. It forms an ideal. So then you can ask questions like, is this ideal finitely generated? Can you characterize this ideal? What are the polynomials that generate this ideal, and so on? So such questions are reasonably well studied in polynomial identity theory. It has some applications to randomized PIT in algebraic complexity. So that's all. I think I did overshoot a little bit. Thank you.
Any questions? There seem to be no questions, so that can be.
This was your pen drive, right? No.
This is mine.
Okay, let me just start the recording. You can.
How do I?